Okay, hello everybody. And I'm sorry, but Q is not a quantum. This is a quadrature, but it's funny. Okay. Okay, my presentation is related to the Q information geometry of systems, and okay, and the outline of the talk is a classical introduction, and we will develop Q information geometry and experiment results and conclusion and perspective. Okay, and the first part of the Q information geometry is a system identification. System identification consisting to obtain in a final map a best parametric model using the third step estimation and validation from measurements. The classical process of the system identification. Okay, this is the first step. Okay. And now we define the information geometry of system. And the first step is to define a parametric model, as you can see. And there are a process model, IG, and a noise model as H. And this is the representation of the classical. Okay. And Z and Z bar are zero poles of parametric models of process and noise. And the second step is to define a manifold of system from power spectral density as a phi. And the points of this manifold is the power spectral density. Okay. And you can see different calculus of expression of power spectral density. Okay, and parametric model manifold, and the final step is to define a metric on manifold between two adjacent system models, and we use in fact the logarithm of the power spectral density as the capstone. Yes, this is a classical tools in signal processing. Okay, and in fact there exist two kinds of system in the literature. Minimum phase system is a system where all zero poles inside the unit disk. Okay, and in 2015, Choi and Mirop has developed the specific Calais information geometry only related to minimum phase system, and they conclude that the information geometry was a Kählerian, was a metric composite only one metric tensor, and as the second derivative of the potential Kählerian. Okay, and what happens when there are when we are a maximum phase system? A maximum phase system is a system where some zero in transfer function are outside the unit disk. And in fact, what information geometry? Manifold, tensor matrix. Okay, this is the Q information geometry that I developed. Okay, this is the main process of the Q information geometry. And the first step is to choose the parametric system model. And after we define a different power spectral density as named joint power density as the square of the product of the power spectral density of process times power spectral density of noise. And after we put the Capstrom as the logarithm, and after we define a psi function as the derivative of the Capstrom with respect to z mu, and z mu are 0 and poles. Okay, and after we define the Q manifold of system as this, with we organize the joint PSD, power spectral density, with condition for convergence. Okay, and after we are two cases. Okay, and minimum phase system and maximum phase system. Minimum phase system with J equal 1, and this is the Cho-Mulrop approach. Okay, and for maximum phase system, for J equal to 3, we define another expression of complex Lagrangian like this, and minimum phase is 1 metric tensor, maximum phase is 4 metric tensors. And we can see that there are two parts of complex Lagrangian and Hermitian parts for pore 0 inside the unit disk, and non-Hermitian for 0 outside the unit disk. And omega is the Finsler coordinates as the derivative. In fact, in origin, the Finsler coordinates are the velocity, and in this approach, omega Finsler coordinates can be used with okay, yeah, with sorry, with Cho is the Finsler parameter. Okay, and in fact, the Q information geometry related to Q space is connected with the R-Complex Finsler spaces theory developed by Monteanu, Porcaro, Aldea in 2010. Okay, and in fact, we develop a context of the Q information geometry. This is a real complex Finsler space with a pair of manifolds and a metric. And we recognize omega and the Finsler coordinates. And after we define a Q matrix structure, mixing Hermitian part and non-Hermitian part, and the Q metric, and this is the expression, the general expression of metric tensor, okay, and including the psi function, okay, and the Q graph. This is a new graph which represents the model trajectory with respect to the Finsler parameter, and the Q space, the holomorphic tangent bundle, Q space, and the Q Lagrangian as the square of the Finsler metric. Okay, and in fact, with minimum phase system, there is one metric tensor, okay, and with only one parameter defined by alpha equal to 1, okay. And for maximum phase system, there is a metric with a new signature and the plus minus as here, and we are in fact 4 metric tensors, and the Hermitian metric tensor is a square, and non-Hermitian tensor as not square. Okay, it's after difficult to to find the inverse. Okay. In fact, to apply this point of view, this new approach of information geometry for a maximum phase system, in fact, the propagative system are sometimes in transfer function some zeros outside the unit disk, and this is the system identification plant, and this is the real view of this system. And from microphone, we estimate and validate a parametric model using an estimator such that M estimate. And in this approach, Cho is the Finsler parameter equal to slope and threshold of the cost function of the defined by this expression, and we see that tau is here, and this is the slope and threshold. Okay. And this is the setup of, in fact, the J is the transfer function of process, and we see a Z mu zero. Z mu zero is the zero outside the unit disk, and Z mu high is zero inside the unit disk, and Z mu p, this is the polar, always inside the unit disk. Okay, and we took 40 values of Finsler parameter, Cho, and okay, and this is here. This is the 4 expression of metric tensor for our example. Okay. In fact, just to summarize this approach, we can show that the Q graph named model trajectory, and each point is for one value of Finsler parameter, and you can see that for 3 exogenous zero, exogenous is zero outside the unit disk, and 3 exogenous zero, the Q graph is here, and you can see in this area the very best model. Okay, and for 4 exogenous zero, the Q graph is different, but we remark that in this area near zero, we have a very best model. Okay, and in fact, the Q graph is a Z-plan. The axis plan, the real axis plan, the real axis is the Hermitian metric, and the imaginary axis is the non-Hermitian metric. But these 2 axes is in quadrature. Okay, and here we show the frequency response of, and we can see a very good model. And for this system in automatic control, in fact, the best model is important in low frequency, and you can see that frequency response is very good for 3 exogenous model and 0 and 4 exogenous zero. Okay, and conclusion, we define another approach of the information geometry of signal processing of systems, and the Q information geometry is a generalization of the information geometry of system, and you can see that the Q graph is a fundamental aspect to see different system minimum phase and maximum phase, and and after to the future, and there is many investigations, and the first investigation is to analyze a non-linear and linear connection and the Chern-Finsler connection, and analyzes the geodesics on the manifold, the curvatures, and maybe analysis metric such that renders metric and Kropiner metric, and okay, and this is the bibliography, and in the end, this is the R-Complex Finsler spaces developed by Monteanu, Aldea, and Porcaro. Okay, thank you for attention.
Are there any questions?
A question?
Yes. Sorry for the queue.
Okay.
Yes, can I ask a question?
Yes.
Yes, so you were showing at some point like a potential. So I was wondering, what is the freedom in choosing this potential, right? For your Taylor form. You see my question. Is that I forgot what is the, I'm sorry.
Yeah.
Phi, whatever.
Yes. In fact,
you think it positive, definitely, I assume, because you talk about Taylor, right?
Yeah.
Yes.
Yeah.
So it's chi, I think. Right.
Yeah.
Yeah, but can you choose it? I mean, you really have no conditions on that except the positive data.
No.
Oh, thank you.
No. In fact, Cho and Murop show you that in fact the metric tensor is a Hermitian tensor. Okay.
Okay.
And show that they came on this relation on second derivative of the potential of the Kähler potential as with no condition.
Okay, thank you.
With no condition. Yes, this is a surprising result, but it's very important. But I try to have a same result of new potential, but no,
Okay.
it's not, because the problem comes from the non-Hermitian part in the Q information geometry with J equal to 3, because this is a real problem for me. Yes.
Well, just in the continuation of your question, but maybe you have anyway some symmetry consideration in the choice of your Kähler potential.
Exactly, that was.
Maybe.
Most of the Kähler potential, they have very strong symmetry in terms of classical domains,
Of course, yes, of course. Actually, if you pose the symmetry, yes.
Yes, you agree. Yes, there is a simplicity. Yeah.
So you're not looking at that.
Yeah.
Okay.
And
Is there any other question? Okay, so let's thank the speaker again.
Yeah.